this one here, if people are not paying attention, they're going to have a hard time, because this question here, this image here is not part of the question. I'm not sure what happened. I'm not sure if whoever did this sheet got it from a different place, but you can see that this temperature is given in Fahrenheit. This one is Fahrenheit too, and this one is in Celsius. So when you're solving this, forget about this image. I'm going to redraw this system for us, okay? So that's probably the hardest thing on this question, because this image does not go with it, so it just throws you off. So 118. Air enters a window air conditioner at atmospheric pressure. 36 degrees dry bulb temperature, that's the air temperature that we've been using, and 65% relative humidity. It's cooled to 10 Celsius at constant pressure below its dew point temperature. Determine the rate of heat removal from the air. Okay. So what we have here is exactly the same as we had before, right? So we're going to have okay, we have an AC, and we're going to have a cooling coil, like the one that's on the line above. And then we have an inlet and an outlet. Now, we don't have, this problem doesn't give us any volume flow rate, mass flow rate, anything we can use for that matter. So there's no way we can find any mass related properties here on this problem, okay? But we're after the Q, so we can just leave that mass flow rate on the equation as we go. What we do know is that we have a certain energy being removed, so we have the Q leaving here. We have water leaving here, so this is water leaving this right here. We have air on this end here, which is the output of the AC, and we also have air on this end here. Now, on this side, we have temperature of 36 Celsius, and we have relative humidity of 65%. On the right side, we have a temperature, and I'm going to call this T2. And I know T2 is temperature of the dew point minus 10 Celsius. That's all I know about it. Okay, so as it's going from this end to this end, it enters at 36 and it leaves at a temperature that is 10 degrees colder than the dew point. Okay, so if that's the case, right, think about it this way. At this point here, after I went through the coil, temperature is temperature dew point minus 10. Now, if it's 10 degrees below the dew point, what does that mean? It means that is 100% saturated, right? It's 100%, its relative humidity is 100%. Because the dew point temperature is precisely the temperature at which the condensation begins when the air is cooled at a constant pressure. That's literally the definition of the dew point temperature. So if I have a temperature, my T2, since it's be like this, since my T2 is smaller than my temperature dew point, and I don't even know what that temperature is, I just know it's smaller because the temperature is slower than that. And then T2 is 100%. Okay, so we have water leaving at T minus 10, we don't know that yet. We have air leaving at T dew point minus 10, and we have the desired properties of the inlet. So we can combine this all, right? We have pretty much defined all the three states. We have two things for each state. So we can find what is the temperature of the dew point using these two properties here. Find what's the dew point temperature for this guy here, and then find T exit. And with that, calculate what we need to calculate. It's really straightforward question. So let's first off grab the properties of the psychrometric chart or the psychrometric calculator. I'm going to be looking at a dry bulb temperature of 36 and a relative humidity of 65%. And then I'm going to grab following properties. Temperature of the dew point under these conditions is 28, about 28 Celsius. My enthalpy is about 99 kilojoules per meter. My omega, the amount of water that I have for every kilogram of air, is about 24.5. Right. So if dew point is 28, that means that my exit temperature is 18. And with 18, knowing that it's 18 and relative humidity is 100, we go to 31, let's grab the properties. We got my H state 2. Let's actually put down what state is it. State 1 and state 2. H2 is 51 kilojoules per kilograms. And my omega 2, 30 pounds per kilogram. What else? Water is leaving, it's being condensed inside the AC and leaving at 18. So how can we grab properties of water? We need enthalpy of water as a saturated liquid at 18 Celsius. That's easy enough for us, right? We can grab HF or HSAT liquid at 18, which equals, I had to interpolate for this one, okay? I got interpolate to about 76 kilojoules per kilogram. So I had to interpolate between 15 and 20, just so you know. Okay, so I have enthalpy for all the states. I have all the states defined. It's just a matter of calculating what is that Q there. To calculate that Q, let's do it in parts. Okay, so let's do energy balance. What do we have? We have the little AC there. Then we have incoming in energy enthalpy 1, outcoming 2. We also have leaving water and leaving energy. So H1 has to be equal to H2 plus enthalpy of water plus leaving energy. The leaving energy is equal to H1 minus H2 percentage of leaving water. If I want a rate, I'll multiply everything by mass per rate. So that means that my Q as a rate is going to be equal 1 minus H2 H2 minus mass per rate water. What do we have at this point in time? We have this guy, we have this guy, we have this guy. We don't have this guy, we don't have this guy, we don't have this guy. So let's just see what we can do about it, because we can't find them as numbers because we don't have any information related to mass, right? So we can do, okay, again, same thing, same logic as before, right? We have air entering this guy here and then leaving over here. We don't have air breaking up and leaving down with water. So that means that mass balance is here. So my mass flow rate of 1 has to be equal to my mass flow rate of 2, because no air leaves with water. Okay, what else? Do H2O gas balance. What do we have there? We have a little AC, and we have water that's coming with the air here, and that water is the flow rate of air times omega 1. And it's leaving, so we still have some water when it leaves. Omega 2. We also have the water that's leaving. as saturated liquid. So a water mass balance is going to tell us that. So therefore, whatever water we had in the beginning has to be equal to the water that's been split up. Okay, if M1 and M2 are the same, that means that my mass flow rate of water equals my mass flow rate 1 or 2, doesn't really matter, of omega 1 minus omega 2. So I can do this over there. And what I'm going to do is I'm going to push these guys downward so we can just continue calculating again. This is one of the perks of not using a paper-based thing. Okay, so I can do using this relationship that we just found. I can put it in here, so that means that my Q dots will be M1 H1 minus H2. And I can sub in that mass flow rate for M1 omega 1 minus omega 2 times enthalpy of water. So no M1 is multiplying everything, so I can do M1 that multiplies H1 minus H2 minus multiplied by M1 minus omega 2. Okay, and I can finish this off. Again, I don't have M1, and there's no way of getting it. So I can do this, and I can do H1 minus H2 minus H water times omega 1 minus omega 2. That's as far as I can go to find and finish off this problem. Okay, we have, let's see, this guy, 99. This guy, 51. This guy, 76. This guy, 24.5. Kilograms, so I need to convert it. And this guy, 13. Let's go ahead and do, instead of 24.5, let's do 24 times 10 to the minus 3. Kilograms per kilograms. This guy, 13 kilograms per kilograms. So that way, we're all on the same page. Oops. Times 10 to the minus 3. Okay, so my Q dot over my QM1 equals dot 27. Let's check the units, right? Because this is one thing that we might get wrong in the very end of it. Okay, this is my energy that's being removed. Okay, let's check the units. Let me zoom in here. Enthalpy 1. Enthalpy 1 is kilojoules per kilogram of air. Enthalpy 2. Kilojoules per kilogram of air. Enthalpy 3. That is kilojoules per kilogram of water. Times kilograms of water for every kilogram of air. So water cuts water, and we're left with kilojoules per kilogram of air. Okay, so it's 47. The amount of energy to be removed is 47 kilojoules for every kilogram of air that's going into my air conditioner. Okay, not to be confused with the fluid of water. That's pretty much it for this one, believe it or not. As I said, it's not that hard. Any other questions?